Welcome to the video lecture on integration by parts. Integration by parts is a technique of integration that is used when integrating products of algebraic functions with transcendental functions, such as the integral of x ln x, or the integral of x squared sine x, things with inverse trig functions inside of them, things with odd powers of cosecant and secant, and the natural logarithm function. So think of integration by parts as kind of like a product rule for integrals that you're typically going to use when you see a product of algebraic functions, which basically means powers of x, times ln's, trig functions, inverse trig functions, things like that. Okay, so let's recall what the product rule for derivatives says. So if you wanted to take the derivative with respect to x of a function u times a function v, where u and v are implied to be functions of x, then the product rule says that this is going to be the first function, which is our u, times the derivative of the second function, so that would be the derivative of v with respect to x, plus the second function v times the derivative of the first, which would be the derivative of u with respect to x. So if this is our derivative rule, then if I integrate the right-hand side, I should get back the left-hand side. So that's what I'm going to do here. I'm going to sort of multiply both of these sides by a dx. So I'm going to take this u dv dx plus v du dx, and I'm going to multiply all of that times dx and integrate it. And I did that exact same thing on the left side as well. I put in a dx and an integral sign. So basically all I'm doing is integrating both sides. Now this dx and this dx essentially cancel each other out, so we're just integrating the derivative of u times v, which should just be u times v. The integral of a derivative, those cancel each other out. So the integral of the derivative of uv is just uv. So that's our left-hand side. On the right-hand side, if I go ahead and I distribute my dx across to each of these terms, again, the dx are going to cancel for both of them. So we'll get the integral of u dv plus v du. And I'm going to go ahead and distribute that integral symbol. So this becomes the integral of u dv plus the integral of v du. And what I'm going to do next is just subtract this integral of v du over to the left side. So the left side will be that uv minus the integral of v du, and that equals the integral of u dv. So this looks like a foreign language right here because of all these u's and v's and du's and dv's, but this right here is the rule that we use when we are going to do integration by parts. So you're saying to yourself, well, what does that mean? What do we do with this? What you're going to be given in the problem is this right-hand side. So in your integral, you're going to assign part of what's inside to be the u, and part of what's inside your integral to be dv, and you want everything to be accounted for. So everything in your integral, including the dx that's in the integral, is going to be assigned either the u part or the dv part. And then what we're going to do is find out these other four pieces. So we'll know what u is already, so from that we can figure out what the du is. We'll know what our dv is, so we'll integrate that to figure out what our v is, and then we're going to plug in to this left-hand side to get our answer for what the integral should be. So it's going to be the u times the v minus the integral of v du. So this is essentially the formula that you're going to be using throughout this lecture right here on integration by parts. So for example, suppose that you have the integral of x e to the x dx. What you're starting with is this left-hand side. So this is your u dv. So what you want to do initially is you want to assign something inside of here to be your u, and something inside of here to be your dv. Now the dx always has to be a part of the dv because those are going to represent the derivatives of something. So the dx always goes with the dv part. Now the question is, should I let my u be x? Should I let my u be e to the x, or should I let it be the x times e to the x, or what? What are my choices here, and what would be the best choice to make? So here are some hints. Typically, we try to pick our u to be the part of this original function that is going to become simpler after we take its derivative, because that's what we're going to do eventually here. Once we figure out what our u is, we're going to find out what its derivative du is so that we can use it in this formula. So typically, you want to pick your u so that du becomes simpler. Another hint is that whatever you assign your dv to equal, we're going to need to integrate that to find out what the original v should be. So you only want to pick your dv to be something that you know how to integrate. So I've got choices here. X, if I take the derivative of that, that just becomes a 1, which is very simple. Likewise, if I look at e to the x, the derivative of that is going to stay e to the x. So that's not really getting simpler. So for that reason, I'm going to choose my u to be the x. Therefore, the du will be the derivative of x, which is just 1 times dx. Okay, so all I did was I took the derivative of both sides using that differential notation. Now, if I am letting the x be the u part, then that means this e to the x dx is my dv part. So it has to be something I know how to integrate, and I do know how to integrate e to the x. The integral of e to the x is just e to the x back again. So that means v is going to be e to the x. So these are the 4 things you need to find. Your u and your dv, those you assign from the original problem. Once you assign those, then you're going to figure out your du and your v. You find du by taking the derivative, and you find v by taking the integral. Once you have these 4 pieces, then your formula for integration by parts is that this integral, which is this left-hand side of this formula, equals u times v minus the integral of v du. And you're probably going to need to write this formula down a few times when you're first starting out these problems until you memorized it. So we want our u, which is this x, times our v, which we figured out was e to the x, minus the integral of our v again, which again was that e to the x, times our du, and du was just this 1 times dx, or just dx. Your goal with integration by parts is, after plugging in these 4 pieces into this formula, the integral that you're left over with here should be simpler and easier to solve. And ideally, it should be something you can integrate right away and be done, which this one is, because the integral of e to the x is just e to the x back again. So this x e to the x out front stays put. We have a minus in between. The integral of e to the x is e to the x. No more integrals are present, so we're done as long as we put a plus c on the end. So the integral of x e to the x dx is just x e to the x minus e to the x plus c. And this one, again, was a product of a algebraic function, the x part, times one of these transcendental functions, that e to the x part. Okay, so let's go ahead and try another example. Very similar to the last one, but this time I'm bumping up that power on our x. So now it's an x squared. So this is the integral of x squared e to the x. Now remember again that this is going to be your u dv. So part of this is our u and part of this is our dv. So we need to assign u to be something and dv to be something. You want to try to pick your u so that when you take its derivative, it gets simpler. So again, if I let my u be that x squared, then du would make this derivative become 2x, and then you're going to put that dx next to it. So we took a quadratic function and we made it simpler by turning it into a linear function. If I let my u be the x squared, then that means the rest of this, the e to the x dx, has to be my dv, because everything needs to be used. I can't leave any pieces out. So if I have dv is e to the x dx, then what was the original v? Well, it would be the integral of this, and the integral of e to the x is just e to the x back again. So now that I have my four pieces, our formula for integration by parts is that this is u times v minus the integral of v du. So this is going to equal u times v. U is x squared, v is e to the x, minus the integral of v, which is e to the x, times du, and du is 2x e to the x. So this looks like x squared e to the x minus, I'm going to go ahead and pull that 2 out, and I'm going to put this x in front. So I'm left with, let me space it out here just a little bit better, 2 times the integral of x e to the x dx. Now, the idea behind integration by parts is that after you apply this formula, the integral that you have left here, we're still not done until we've solved this integral. Hopefully it's something that you can integrate right away and be done, or at least that it's simpler. So do we know how to integrate x e to the x dx? No, we don't, at least not initially by any of the previous rules that we've learned. If I just had the x or I just had the e to the x, I could do this. But x e to the x is exactly the problem we just did in example number 1. So you can either use that result, or what you'll notice here is essentially what we're doing is we're going to apply integration by parts again. And you're allowed to do integration by parts as many times as it takes so that you keep reducing this integral down to something simpler and simpler until eventually you can solve it completely and there's no integrals left. So what we're going to do when we get to this point is, if we didn't already know the result from example 1, we would do integration by parts again. And that was where we let the u be the x part and the dv be to the e to the x dx part. So du, the derivative, is just 1 times dx, or just dx, and v is the integral of e to the x dx, which is just e to the x. So applying the formula again, but now to this, gives me u times v, so x times e to the x, minus the integral of v du, so e to the x dx. Now you want to be a little bit careful here about what you had in front. We still have this x squared e to the x in front, and then we had a minus 2 in front of that entire integral. So don't lose that. So now let's see what we have. We've got x squared e to the x minus 2 parentheses x e to the x, and now this integral is something we know the answer to. The integral of e to the x is e to the x back again, and that minus stays out front. So no more integrals are left. Let's just distribute our negative 2 across to kind of clean it up a little bit. This becomes x squared e to the x minus 2x e to the x, minus times minus becomes plus 2 e to the x, and I'm all done integrating, so I'm ready to put my plus c on the end. And there is our final answer. So you are allowed to use integration by parts more than once, as many times as it takes until you can get to an integral that you know the answer to. Alright, the next example here, the integral of e to the x sine of 2x dx. So when you look at this, how do you know that this should be an integration by parts problem? Well, the fact that it's a product, because integration by parts is really the product rule applied to integrals. So this is a product of e to the x times sine of 2x. So that's kind of your clue that using integration by parts is the strategy to use here. So again, this is going to be your u dv. So you have to make a choice as to what you're going to let the u be and what your dv is going to equal. And on this particular problem, there's more than one correct way to do this, and that happens a lot of the times with these integration by parts problems. You can choose your u to be the e to the x, or you could choose your u to be the sine of 2x. Both options work perfectly fine. Now, personally, I think taking the derivative of sine of 2x is easier to do than to take the integral of sine of 2x. So based on that, I am going to assign my u to be the sine function, and that means the e to the x and the dx are going to be the dv part. You have to use everything in here and assign everything to either u or dv so that everything's accounted for. So if I make these choices, then du will be the derivative of sine of 2x. Now you need your chain rule on that. The derivative of sine is cosine of the same 2x, but then we have to multiply that by the derivative of 2x, which would be a 2. So I'm going to put the 2 in front, and then we need that dx on the side. To get v, we integrate. The integral of e to the x is e to the x back again. So now I've made my choices, so let's use our formula. This is going to be u times v minus the integral of v du. So u is sine of 2x and v is e to the x. I'm going to put the e to the x in front. Minus the integral of v du. So here's my v and here's my du. So we want to multiply these two together. So we're going to get 2 cosine 2x times e to the x dx. And just to rewrite that a little bit cleaner, I'm going to pull the 2 out. So this is minus 2 times the integral of, and I'm going to put the e to the x in front. Now look at the integral you ended up with. What you're trying to see is if it has now left you with something simpler to integrate or something that you know how to integrate. And this is another product again. It's a product of an e to the x times a trig function. It's almost identical to the original problem. So does it look like we made any progress? Not really. But think about this for a moment. Suppose you were to do integration by parts again, a second time, on this particular function. What do you think this is going to turn into based on what happened when we did it once? Well, when we integrated by parts once, this integral turned into the same exact thing but with a cosine. So if we were to integrate this again, most likely it's going to turn into this same integral with an e to the x, but the cosine is going to flip back into a sine. So that may sound like we're kind of going in a circle, and it is. We actually are going in a circle, and it's going to actually help us. So let me show you. You probably wouldn't think of doing this on your own the first time you do this problem, but it's actually something pretty slick that happens. So what we're going to do is integration by parts again on this integral right here. And what I'm going to recommend is to make the same kind of choices that we did up here so that we're consistent. So up here I let my u equal the trig function. That's what I'm going to do again. So I'm going to let my u be this cosine of 2x, and I'm going to let the dv be the e to the x dx. So then du would be the derivative of cosine, which is a minus sine of 2x, times the derivative of 2x, which is a 2. So we're going to get a negative 2 sine of 2x, and then we'll get that dx as well. Then the integral of dv is the integral of e to the x, which is just e to the x again. So now we're going to apply this formula again to these four choices. So u times v would be e to the x times cosine 2x minus the integral of v du. So we're going to get that negative 2 sine 2x times that e to the x dx. Now all of that is being multiplied by this negative 2 that was out front. Okay, now let's clean it up just a little bit here. This is going to equal e to the x sine of 2x. We're going to get a minus 2 e to the x cosine of 2x. Minus minus here becomes plus, but when I distribute this negative 2 across, we're actually going to get a minus 4, which I'll pull out of my integral, and that'll leave me with this e to the x and sine of 2x still inside of the integral. So this integral is not simpler, and it's still not anything that I know how to integrate yet. But the good news is it's actually the same exact integral as what we started with. So you might say, well, okay, that means it doesn't work because we didn't make any progress. But here's the slick thing that we're going to do. This answer so far is the answer to this original integral. So let me write it over here on the left-hand side. This is what we got for this integral so far. Now think of this as an equation. This is what we're trying to solve for, and we have that same exact expression over here on the right-hand side. So let's get these two integrals together, and I'm going to do that by just adding the opposite. So I'm going to add 4 times this integral to the left and the right side. So if you have 1 apple plus 4 apples, that makes 5 apples. So that makes 5 of these integrals. 5 times this integral. And because I've added this to the other side, this is now gone from the right-hand side. And so the left side is just this e to the x sine of 2x minus 2e to the x cosine of 2x. Okay, now how does that help me? Well, if we want to solve for this integral, what do we have to do to get it isolated and by itself? We just have to get rid of that coefficient, which we can do by dividing everything by 5. So by solving this equation, we have just found that this integral equals e to the x sine of 2x divided by 5 minus 2e to the x cosine of 2x divided by 5, and there's no more integrals over here on the right hand side to solve. So we have figured out what this answer is. All we need is a plus c. So this is integration by parts. We did it twice, and we did it twice so that we could get back to the original integral and then add it over to the other side, combining those coefficients and then dividing by that coefficient. So this is kind of a tricky process here, what we did, but it was using that cyclical nature of the trig functions and their derivatives, so that by using integration by parts twice, we were able to go from sine to cosine back to sine again, so that we could then combine our integrals on both sides and get it isolated. All right? So you'll see that kind of a problem quite often. It's a pretty common type of integration by parts problem. All right, let's try an integration by parts problem that involves some ln's. So this one is the integral of ln of x dx. Now normally when we think about integration by parts, we're thinking about a product of 2 or more functions, and this is just one function, ln of x. But integration by parts is also used successfully whenever you have an ln function inside of your integral. So look for that. If you're not quite sure how to integrate something that has an ln inside of it, then you might want to try using integration by parts. So this is supposed to be the integral of u dv. So we need to assign our u and our dv. Now it looks like there's only one function in here, ln of x. So that is actually going to be our u, but that isn't the only reason why you want to choose your u to be the ln of x. We wouldn't want to let our dv equal to ln of x, because to find v, that means we'd have to integrate ln of x, and that's exactly what we don't know how to do, because that's what this problem is asking us to find. We don't know what the integral of the ln of x function is. We do know what its derivative is. So you have to let your u be the ln of x function, because we don't know how to integrate it. So if we let u be ln of x, then what is left here for dv? Well, the only thing left is the dx part. So du then would be the derivative of ln of x, which we know is 1 over x times that dx. If dv is just dx, then what would be the integral of that? What's the integral of just dx? Well, that's just the integral of 1, and the integral of 1 is x. Okay, so the integral of 1 dx is just x. So now we have all of our 4 pieces that we need. So our formula says to take u times v minus the integral of v du. So this integral is going to be u times v, so x times ln x, minus the integral of v du, so x times 1 over x dx. And those x's cancel, so after I simplify, this is just the integral of dx, or 1 dx if you want to write that 1 in there. And what is the integral of dx? Well, we just did that over here to find our v. The integral of dx is just x. So that is something we know how to integrate. All the integrals are gone, so we tack on our plus c, and there's our answer. So the integral of the ln function is x ln x minus x plus c. So if we take a look at this next example, it also has an ln in it as well. But I want you to be cautious here. Just because you see an ln of x in your integral, that doesn't always mean that you have to break out your integration by parts formula. Sometimes you don't need it. And how come I don't need it on this particular problem? Because, and hopefully with enough experience, you'll be able to see this easily, with a little bit of substitution, sort of in the back of your head, think about what you know about ln of x. The derivative of ln of x is 1 over x times dx, and that's exactly what I have right here. So this is kind of like our du right here. So that's why we do not need any kind of integration by parts here. We're just going to do simple substitution. We're going to do a u substitution, where we are going to let our u be that ln of x function, but du then would be 1 over x dx, which is exactly what I have circled in red. So that stuff in red becomes our du, and the stuff in the denominator just becomes u cubed. And that is an integral I know how to do because that's just u to the negative 3. That's a power rule. So when I add 1 to the power, it becomes negative 2 divided by the new power. If you want, you can rewrite that as 1 over negative 2u squared. And then substituting back in terms of x, this is just 1 over negative 2 ln of x quantity squared. And finally, we can put in our plus c. So just because there's an ln of x in your integral doesn't imply that you have to use integration by parts. One of the things that I typically look for if I see an ln of x in an integral is, do I also have 1 over x present? Because if I do, then that means it's probably going to be done with a u substitution. If I don't have a 1 over x present, like in this problem, then that's when I'm going to have to use integration by parts. So look for that du, look for that derivative 1 over x. If it's in there, then you could probably get away with just doing a u substitution, which is typically faster and easier to do than integration by parts. Okay, next example here, the integral of x cubed e to the x squared dx. So on this one here, we've got a product of x raised to a power times an exponential function. So there's kind of that product rule. So that's kind of a clue that this is most likely going to be integration by parts. So this that we're given is a u dv right here. So we need to assign our u and we need to assign our dv. Now you have choices here. If you let your u be x cubed, then the derivative of that would be 3x squared, and it's getting simpler. But as you might recall from a previous problem that we did, I think it was example 2, when that power was an x squared, we had to do integration by parts twice to get that power down to an x to the first, and eventually get it down to a constant so that we could integrate it. So if this is a cube, that means we're going to have to probably do integration by parts a few times to get it down to something we can integrate. So that might not be something you want to do. Another thing to think about is your e to the x squared. If you let your u be the x cubed, then that would force you to let your dv be this e to the x squared dx. Do you know how to integrate e to the x squared dx? That is e to the stuff, right? And the only way we know how to integrate e to the stuff is if you also have present in that integral stuff prime. And the derivative of this stuff, the derivative of x squared, is a 2x, which I don't have in here. So the only way to make this work would be if I had an x in here as well, and then we can fix it so that we adjust by some constants so that we get the correct stuff prime. So in order to let your dv include the e to the x squared, you're also going to need to include one of the x's so that you have the correct stuff prime. Which means if I take one of these x's away from this x cubed, then that means I only have an x squared for my u. Okay, so I've used two x's here and one x here, so that's all three. And then I have the e to the x squared dx over here as well. So everything's been accounted for. So this is good for us because not only do I have a smaller power on x so that its derivative becomes linear, which is going to make it simpler faster than before. So that's good news. But now I am able to integrate this, and let's just do that with a little bit of scratch work on the side here. How would you integrate x e to the x squared dx? Well, the correct stuff prime should be a 2x because the derivative of x squared is 2x. So if I put in a 2, then I have to counterbalance by a 1/2. So that 1/2 would stay put. Now, once you have the correct stuff prime, you don't actually do anything with it. It just needs to be there. This is pattern recognition right here. So that 2x needs to be there, but you don't actually integrate it. The integral of e to the stuff times stuff prime is just e to the stuff back again. So this is just going to be that e to the x squared back again times that extra 1/2 that we had to get counterbalance by. So the v here, the integral of this, is 1/2 e to the x squared. The 1/2 is coming from that counterbalancing. All right, we now have our four pieces. So our formula is u times v minus the integral of v du. So u times v is x squared times 1/2 e to the x squared. Let me put the 1/2 in front, and then I have that x squared e to the x squared. So there's my u times v minus the integral of v, which is that 1/2 e to the x squared, times du, which is this 2x dx. So cleaning that up a little bit, the 1/2 and the 2 cancel out, so we have x e to the x squared dx. You're in good shape if this is something that you know how to integrate, and this is exactly what we had originally with our dv. I can integrate this because e to the stuff is this e to the x squared, and stuff prime wants to be a 2x. So we put in our 2, we counterbalance by our 1/2, and that means that minus 1/2 stays out front. And now I have e to the stuff times stuff prime. The integral of that is e to the stuff back again. So e to the x squared back again. So bringing down our stuff in front, here we have our answer. There's no more integrals left, so we're ready to put in our plus c, and there's our final answer. So sometimes on these you have to break up your power of x and use part of it in your dv so that it's something you're able to integrate. All right, let's try the integral of x squared cosine x dx. So again, this is a product. It's a power of x times a trig function. So that's kind of what you're going to look for to decide, should I use integration by parts? Yes, because this is a product of a power of x and a trig function. So we want to assign part of this to be our u and part of this to be our dv. So you could let your u be the x squared, or you could let your u be the cosine of x, either one. I usually, most of the time, let my u be that power of x so that when I do my du, its power gets smaller and therefore simpler. So that's what I'm going to do here. I'm going to let u be x squared so that du becomes 2x dx. That means my dv is the cosine x dx, and that thankfully is something I can integrate. The integral of cosine x is just sine x, and I don't need any negatives there. Okay? So then this is going to be u times v minus the integral of v du. So this becomes x squared times sine x. That's that's my uv, minus the integral of v du, so 2x sine x dx. We can pull that 2 out, and if you look at that, it's still not something I can integrate because it's still a product of a power of x times a trig function, but at least the power on the x got simpler. It's no longer a square, it's a first degree. So we've made some progress, but because it's still a product, that means we can try integration by parts again and hopefully get that power of x down to a constant so that it's no longer there. So we're going to do integration by parts again. Usually when you're doing integration by parts a second time, you want to make the same choices that you made the first time round to be consistent. So if you let your u be the power of x up here, you want to let your u be that power of x again. And if you let your dv be the trig function, then let your dv be the trig function the second time as well. So my du goes down to 1 times dx, or just dx, and my integral of sine x would be negative cosine x. This time I do need that negative. So applying our rule, I'm going to put that minus 2 in front and use parentheses and put the answer in these parentheses. So u times v will be negative x cosine x minus the integral of v, which is this negative cosine x, du, which is just our dx. So if you look at that integral, we've got a minus minus, which I'm just going to make a plus, and this is something simpler now because now that power of x is gone. And I do know how to integrate cosine of x. That's just sine x. No negatives needed. So all I need to do now is just distribute my negative 2 across to kind of clean this up a little bit and put on my plus c. So I have x squared sine x plus 2x cosine x minus 2 sine x, and then I have my plus c on the end. And there's my antiderivative. All right, next integral. The integral of ln of 2x all over x squared dx. So here we have another ln function inside of our integral. Remember what we said earlier. If you have an ln in your function, there's really two things to consider. One is that it's going to be an integration by parts problem, because typically that works for ln's. Or it could be just a u substitution problem if you have a 1 over x present, which this one does have a 1 over x present, but it's actually got more than that because it's a 1 over x squared. So that sort of complicates matters here. So there's definitely more than one way to do some of these problems, but because I have more than just a 1 over x, I'm going to try my u substitution on this to see if I can get it to work. So we're going to let this be our u dv, so we want to assign our u and our dv. Now, most of the time when you're doing these integral problems involving ln's, you want your u to be the ln part of the function because we don't know how to integrate ln typically. So the only thing we do know how to do with ln's is take its derivative. So that's why I'm going to let my u be that numerator ln of 2x, which means my dv is going to be the rest of this 1 over x squared dx, which you can think of as x to the negative 2 dx. So if you think of it that way, then it's just a power rule. So it's integral. When I add 1 to the power, it becomes a negative 1 over negative 1, or that is the same as negative 1 over x. If my u is ln of 2x, then du, remember the derivative of ln of stuff is stuff prime over stuff. So this goes in the bottom, and its derivative goes on the top. And that's going to make those 2's cancel out. So this is really just 1 over x, and then we get that dx on the side. So we have all 4 pieces. So this is going to be u times v minus the integral of v du. So u is ln of 2x times v, which is this negative 1 over x, so I'll just put the negative out front and the x on the bottom, minus the integral of v, which is this negative 1 over x, times du, which is this 1 over x dx. So we get negative ln of 2x over x. This minus minus I'm going to make plus, and 1 over x times 1 over x is 1 over x squared, or x to the negative 2. I'm going to rewrite it as a power rule just to make the integration piece easier. So this is something I can integrate because it's just a power rule. I'm going to add 1 to the power, which makes it a negative 1, divide by the new power. If you want, just to make it look nicer, you can make this become minus 1 over x, and then put our plus c on the end. And there is our answer. Okay, number 9 here, we want the integral of the inverse cosine of x dx. Now we haven't done one like this. This is not a product of two things, it's just the inverse cosine of x. But what you want to remember is that integration by parts works with products, it also works well with ln's, and it's also pretty successfully used with inverse trig functions. So that's what we're going to do here. This is going to be our first example using an inverse trig function. So the way that integration by parts works, again, is to let this be our u dv. So since there's only one function here, and we don't know how to integrate inverse cosine of x, we obviously don't want that to be our dv, we want that to be our u. So we're going to assign our u to be inverse cosine of x. I do have a formula for the derivative of inverse cosine of x. It's exactly like the derivative of the inverse sine, but it has a negative. And the derivative of inverse sine is 1 over the square root of 1 minus x squared. Since this is a cosine, there's a negative in front. And then we get that dx on the side. So that's just kind of a formula you need to know. It's one of our derivative rules. We don't use it that often, but sometimes you need to know it. Okay? Now if we let our u be that inverse cosine of x, then what is left for our dv to equal? Well, this was my u, so this has to be my dv. The dv is just the dx part. So what's the integral of dx? Just an x. Okay? So now we have our 4 pieces, and that means this is going to become u times v minus the integral of v du. The u is the inverse cosine x, and the v is the x. So when I multiply those together, it becomes x inverse cosine x minus the integral of v, which is this x, times du. So all of this negative 1 over square root of 1 minus x squared dx. The strange thing about these inverse trig functions is the fact that they take a trig function and they turn into these sort of algebraic functions after you take derivatives. So that's what happened here. We took this inverse trig function, and by taking its derivative, we've turned it into an algebraic function, which hopefully will now be something we can integrate. Now this minus and this minus become a plus, and I'm going to rewrite this as x over square root of 1 minus x squared dx. Now is that something I can integrate? Is that algebraic function something I can work with? Yes. Let me rewrite it one more time just to help you visualize what we're going to do here. I'm going to move that denominator up to the top and change its power to a negative, since it was in the bottom, 1/2 because it's a square root. This is pattern recognition. Your outer function is the power. Your inner function g is this 1 minus x squared, and the derivative of that wants to be a negative 2x. Thankfully I have the x, I'm just missing the minus 2. So now I'll have the correct g prime. But I have to counterbalance by a negative 1/2. So in pattern recognition, if you have all 3 pieces, then the only piece that you actually integrate is that outer power. The other pieces just need to be there, but you don't do anything with them. So when I integrate That minus 1/2 out front that we counterbalanced by stays there. And when I integrate a negative 1/2, that's a power. So you add 1 to the power, negative 1/2 plus 1 becomes positive 1/2, multiply by the reciprocal out front, and what's inside stays inside. So if I clean this up, we get x inverse cosine x, the 1/2 and the 2 cancel, so this just becomes a minus, and the 1/2 power is a square root, so you can turn it back into a square root if you like, and then we're ready to put on our plus c because all the integrals are gone. So we didn't know how to integrate inverse cosine of x, but by letting it be our u and taking its derivative, we turned it into that algebraic function, which gave us some more stuff to work with so that we could then use pattern recognition to get our answer. Okay, our last example here is another one that we haven't done one like yet. This is the integral of secant cubed x dx. Now, a lot of times we will learn other techniques for how to integrate powers of trig functions, and that's actually going to be a future video lecture that you will watch. But integration by parts is a good strategy to use when you have odd powers of secants and cosecants. So this is something that you kind of want to be on the lookout for. So use integration by parts when you have products of powers of x times trig functions or ln functions. Use integration by parts when you're integrating ln's. Use integration by parts when you're integrating inverse trig functions. And use integration by parts when you have odd powers of secant and cosecant. So this is an odd power of secant. So what we're going to do is we're going to let this be our u dv. And the reason why this is going to work for us is because this odd power enables us to break this up into a secant x times a secant squared x. There's all three of my secants, but I'm breaking them up because when I make my choices for what u and dv should be, I want to make sure that whatever I pick for my dv, it needs to be something that I can integrate. And I do know how to integrate secant x. That is one of the formulas that we have learned in the past, but if you recall, it's a yucky one. The integral of secant of x is ln of the absolute value of secant x plus tan x. So that makes it actually get messier, and we don't want that. We want it to get simpler. So look at the secant squared x. Do we know how to integrate secant squared x? Yes, because secant squared x is just the derivative of tangent. So if you let your dv be all of this, secant squared x dx, then the integral of secant squared is just tangent, and that does make it get simpler. So we're using 2 of the secants in our dv. That leaves 1 of the secants for my u. So what's the derivative of secant? Secant x times tangent of x. So now we have our 4 pieces. Use 2 of them for your dv and the leftovers for your u. So now our formula is going to be u times v minus the integral of v du. So u times v will be secant x times tangent x minus the integral of v, which is tangent of x, times du. Oops, I forgot my dx on there. So du is going to be secant x tan x dx. So rewriting that, regrouping it, we have a tangent times a tangent. So this is secant x times tangent squared x dx. Now, how do we integrate that? That doesn't seem to have given us any progress, right? We haven't really made this any simpler and turned it into something we know how to integrate. But there are some identities that we have at our disposal, and what you want to remember is the Pythagorean identity relating tangent squared and secant squared. Tan squared x plus 1 is secant squared x, or tan squared x equals secant squared x minus 1. That's what I'm going to use here. I'm going to get rid of this tangent and I'm going to replace it with secant squared x minus 1. And again, this is maybe something you wouldn't normally think of doing the first time you do this problem, but with practice and experience, you'll kind of learn to know what works and what doesn't work. So by substituting that secant squared x minus 1 in, the reason this is helpful is because when I distribute my secant across, I'm going to get a secant cubed x minus secant x dx. And that secant cubed x, remember, was the same thing we started with at the beginning. So this is kind of like that earlier example we did before, where the integral that we were trying to solve for on the left-hand side ended up showing up again on the right-hand side. It's one of those cyclical kinds of integration problems where if you do enough work, you get back to what you started with so that you can essentially combine the two integrals together and solve for it. And we did that earlier when we had that sine cosine problem. So let me clean up my signs here just a little bit so that we're not going to get ourselves in trouble. I'm going to go ahead and I'm going to distribute this negative across and break up this integral into two separate integrals. So I'm going to have negative the integral of secant cubed x dx, and then minus minus becomes plus the integral of secant x dx. Now this one I know how to do. That was that messy ln of the absolute value of secant x plus tangent x. This one I don't know how to do, but that is what is on the left-hand side over here already. So what we can do to solve for it is think of this as an equation where this integral is sort of the variable, the unknown that we're trying to solve for. So I'm going to get my two like integrals together by adding this guy over to the left side. So the integral of secant cubed plus the integral of secant cubed is 2 times the integral of secant cubed x dx. An apple plus an apple is 2 apples there. So what we have now on the left-hand side is twice what we're looking to find. So how do I get rid of that 2? We just divide, just divide everything by 2. So the integral of secant cubed x dx is secant x tan x divided by 2 plus the ln of secant x plus tan x divided by 2. There's no more integrals left on that right-hand side, so we're done. We just need our plus c. So this is kind of like that cyclical example we did earlier, where if you do enough work, eventually you get back to the original problem, and then you can think of it as an equation, do the opposite to get the two integrals together, and then divide through by that coefficient. Alright, that concludes our video lecture on integration by parts. Good luck!